video, we're going to focus on two main things. We're going to focus on the average rate of change of a function, and we are going to focus on the difference quotient, both of which should be somewhat reviewed to you. So we talked about in the first section how the rate of change of a linear function is always constant. So you could say the rate of change of a line is always 2. With other functions, for example, with a quadratic, the rate of change is different. The rate of change from a point down here to a point here, this, if you found the slope between those 2 points, is going to be different than if you found the slope between these 2 points. The rate of change is not constant, it is changing. And that's where this idea of the average rate of change of a function comes from. So average rate of change of a function, which I'm going to abbreviate AROC, A-R-O-C, is really just talking about the slope. So what does it mean? It's talking about the slope, but we're talking about the slope in a sense that it is not always constant. So since when we're talking about the average rate of change of a function, since that may not always be the same over the entirety of the function, what we can do is we can look at a specific interval, maybe from 0 to 5 or from -12 to 15. We can look at a particular interval and find the average value, which is really just a fancy term for slope, the average value over that particular interval. So how do we calculate that? How do we calculate the average rate of change over a particular interval? So let's say we're looking at the average rate of change given that we have some continuous function f. So given that f is continuous on the interval from a to b. How we would calculate this is we would basically find the slope. So we would find the function evaluated at b minus the function evaluated at a divided by b over a. And this is really just the slope formula. y2 minus y1 over x2 minus x1. The same idea here. So let's look at some examples. Find the average rate of change of the function f of x equals x squared plus 1 on the interval from 2 to 4. So what they're asking us to do, using this formula that we just established here, is to say f of b, which in this case is 4, f of b minus f of a, all over b, which is 4, minus a, which is 2. So let's go ahead and figure out what some of these things are. Let's figure out what f of 4 is. F of 4 is 4 squared plus 1, which is 16 plus 1, which is 17. F of 2 is 2 squared plus 1, which is 4 plus 1, which is 5. So 17 minus 5, all over 4 minus 2, so all over 2. So the average rate of change, 17 minus 5 is 12. 12 divided by 2 is 6. The average rate of change is 6. Now, if we were looking at a different interval, if we were looking at something that was not from 2 to 4, the average rate of change would be different, likely. If we were looking at the average rate of change from 1 to 4, it would definitely be different. So keep in mind that the average rate of change of f of x on the interval from 2 to 4 is 6. So again, we're just looking at a snapshot of a particular interval. Let's go ahead and practice calculating the average rate of change a couple of more times. Now, I encourage you, if you felt like that process was pretty straightforward in that example, I encourage you to pause the video and work through number 1 on your own and then unpause the video and see how you did. If you want one more example to work through with me, then let's go ahead and do number 1 together, and then you can try number 2 on your own. So pause the video if you're ready. So we are finding the average rate of change of the function g over the interval on number 1 from -2 to -1. So how do I do that? I take g of -1 minus g of -2, and I divide it by -1 minus -2. This denominator is going to simplify to be 1. -1 minus -2 is -1 plus 2. And then let's calculate the values for the numerator. G of -1 is going to be -1 to the third, so -1 plus 1, which is 0, minus g of -2 is going to be -2 cubed, which is -8, plus 1 is -7. So this is going to become plus 7, so the average rate of change is going to be 7. I encourage you to pause the video and work through number 2 on your own. So here's the setup. Once we calculate the individual values of the function and then simplify the average rate of change formula, we get 17. So I want you to notice that we used the same function g for both number 1 and number 2. However, those average rate of change are very different, which makes sense. We're talking about a cubic function. So how the slope changes on one part of the function versus another is going to be drastically different. So just keeping that in mind, average rate of change is very much dependent on the interval. All right, the last example we're going to look at is this graph. And we are given the function f of x here. However, we're going to do the best we can to use what we can see in the graph so that maybe we don't have to do this plugging a number into the function step here. So on A, we're being asked to find the average rate of change from -1 to 0, on B from 0 to 1, and on C from -1 to +1. So let's go ahead and identify what we can from our graph. This point is telling me that f of -1 is -8. This point is telling me that f of 0 is 0. And this point is telling me that f of 1 is -2. So looking at part A, we want f of 0 minus f of -1 over 0 minus -1. So the denominator is just going to become 1. Let's use our function over here, these values. F of 0 is 0, so 0 minus f of -1 is -8. So the average rate of change here on A is going to be 8. Go ahead and pause the video and work through B and C on your own, and then unpause the video and see how you did. For B, f of 1 minus f of 0, well, f of 1 is -2, f of 0 is 0. This is going to be divided by 1, so the average rate of change in B is going to be -2. On C, f of 1 minus f of -1 over 1 minus -1. F of 1 is -2 minus -8 over 2. That's going to give us 6 over 2, which is 3. So pause the video if you need to, make sure that you got each of those correct, and then we're going to move on to our last topic for today, which is the difference quotient. So let's think for a moment about a piece of a function, and we'll say that this function, that this is some particular x value, and that this point, the second point, is some h distance away from x. So we could say that this distance here is h. If we were going to use the average rate of change, we would be talking about drawing a straight line between these 2 points and calculating the slope between those 2 points. And this is really the same as finding the slope of a secant line, right? A secant line is a line that passes through a function or a shape twice. And that's exactly what's happening here. It's passing through each of the endpoints. So this here would be our secant line. So if we set up the average rate of change the same way that we just did before, we would say that f of the upper bound of our interval, which is x plus h, minus f of x, the first point, all over x plus h minus x. And this can simplify, since our x and our negative x would add to 0, to be this. And this right here is what we call the difference quotient. So I wanted you to see how it really just comes from applying average rate of change to a secant line and looking at a particular part of a function in a similar way. So really, we're still just finding slope. You could think of the difference quotient sort of as some fancy slope, but let's look at some applications of it and how it works in a more abstract way than just looking at the average rate of change. So here we have our difference quotient, or our fancy slope. And what we're going to be doing is we're going to be looking at the difference quotient in terms of just x and h, and then at the end we're going to evaluate it at a particular value. But I really want you to see how to simplify with the difference quotient even if you don't have a particular h value. So let's walk through this process. Let's start by defining what f of x plus h is going to be in terms of this function f. So that would be x plus h quantity squared plus x plus h, right? Everywhere that there is an x, we're substituting in x plus h. And then we know that f of x, let's use a different color actually. We know that f of x is just x squared plus x. So now if we perform the difference quotient, we're going to have x plus h quantity squared plus x plus h minus f of x, which is x squared plus x, all over h. Let's actually move so we can have a little bit more space here. Here we go. Now we're going to simplify in the numerator. So this is a perfect square binomial, which means if I multiplied it out, I would get x squared plus 2xh plus h squared. And then I'm just going to get rid of the parentheses. And then I'm going to distribute this negative sign. And this is all still over h. And now I'm going to simplify what I can simplify in the numerator. So x squared and negative x is 0. Negative x and positive x is 0. So what's left here? 2xh plus h squared plus h. And all of this is over h. I want you to notice that we actually have a greatest common factor here, and that greatest common factor is h. Let's factor that out. That leaves us with 2x plus h plus 1. And then all of this is still over h, which I can now divide out. H divided by h is 1. So the difference quotient would leave us with this expression here. The next part of the directions here, and actually let's rewrite that back on the other place, 2x plus h plus 1. And then over here, we're being asked to evaluate that when h is equal to 1. So I'm going to draw a little line. This line means when evaluated at h equals 1. And if I substitute 1 in for h, I would get 2x plus 1 plus 1, or 2x plus 2. So the difference quotient can still give us an expression, as opposed to the average rate of change is always going to simplify down to be a number. So we're now looking at an expression that can represent that rate of change. And this is actually a line. This is a linear expression, since it doesn't have an equal sign, that represents the same idea, the same slope, but now represented as a line. And that's going to be a big concept leading into future chapters, where we're talking about slope, or we're talking about the rate of change, but we're not talking about it as a constant value. We're talking about it as a function that is changing as well. But let's focus the rest of this lesson on making sure we understand how to use the difference quotient here. So what we are going to do on number 4 is we are going to substitute in f of x plus h minus f of x over h. So f of x plus h is going to be 3 times x plus h plus 1 minus f of x, which is just 3x plus 1. Don't forget your parentheses, because you're going to end up needing to distribute that negative. This is all over h. If I distribute 3x plus 3h plus 1 minus 3x minus 1, all over h. Let's see what adds to be 0 here. Negative 3x and positive 3x, negative 1 and positive 1. So I have 3h over h, which is going to simplify in this case to just be 3. All right, I encourage you to pause the video and work through number 5 and see how far you can get on number 6. It's possible you're going to get a little bit stuck having to work with some radicals, and I'm happy to help you with that. My one piece of advice is think about conjugates and see if you can reach back into your memory and come up with something that might help you simplify. But at least work through number 5 on your own, and then unpause the video and see how you did. So here's the setup where we plug in x plus h for all of our x's. Now I'm going to multiply out my perfect square and distribute that negative sign. So now we're here, and let's go ahead and combine like terms. And then we can divide an h out, which would give us 2x plus h plus 2 as our expression. I'm going to move number 6 to a new slide so that we have room to work, and then we'll work through that last question. So we would start here by setting up the difference quotient, and now our goal is to simplify as much as possible here, and the best way to simplify when we have radicals like this is to multiply by the conjugate. So if you remember, the conjugate is going to be exactly the same as what you see in the numerator, except you're going to change the sign that's in between these two radicals. And most often in previous courses, you have multiplied by the conjugate in order to rationalize the denominator, and we're actually doing the exact opposite here. But again, our intent is that we find a way to simplify this expression more than it is currently simplified. So when I do this, the numerator, the whole point of setting this up is so that we have the difference of squares in the numerator. So when I multiply this out, the middle terms would add to be 0. What I'm really doing is multiplying these two things and multiplying these two things, since the middle two terms would be the same and opposite sign. So what am I left with? I'm left with the thing inside the blue radical minus the thing inside the red radical. And this is now over h, and don't distribute in the denominator, just leave this sort of messy radical down here. In calculus, we don't really care if there's messy radicals in the denominator of our fraction. You don't have to worry about rationalizing that. So we're going to leave it here, and then we're going to simplify the numerator as much as possible. If I distribute this negative, I would get minus x plus 2. So the x's are going to add to be 0, and the 2's are 2 and negative 2 are going to add to be 0. So that's going to leave me with just h in the numerator, and h times all of this conjugate stuff in the denominator. So my h's will divide to be 1, and my final answer will be the square root of x plus h minus 2 plus the square root of x plus 2. And this may look messier than this expression up here, but the expression that you just created in future sections, when we start taking limits involving these difference quotients, this answer is going to be much more helpful for you. So let's recap what we covered in this section. We first talked about the average rate of change. And the average rate of change is just talking about the slope of a secant line, which is not always constant when we're talking about a function that's not linear. So we're going to be talking about finding f of b minus f of a over b minus a. And we call that the average rate of change of a function, or sometimes it's referred to as the AROC. We worked through some examples on that, and we looked at a graphical representation of doing that from a graph as opposed to just from a function. And then we talked about the difference quotient, or our fancy slope, and how to calculate the difference quotient, whether we are plugging in a specific value or leaving our final answer with h's still included in it. So make sure you write down any questions you have. I look forward to supporting you on this, and thanks for listening.